that's congestion in road networks, and it's kind of similar to computer networking because the cars represent packets, right? And the links are can be viewed as roads. But anyway, today we're going to be talking about TCP, which is an extension of the topic of last lecture, but with more real-world details. Announcements. Project we wanted to do yesterday, as I'm sure you know, there is, if you weren't able to get it done, you can turn it in late if you want. It'll be 10% off per day. So I hope you already have it done. Or if you want to do tomorrow night, don't forget about that. And project 2 will be posted soon, probably this afternoon. So there's no rest for the weird. And project 2 will cover DNS. So it's another application layer project. So last lecture I talked about transport layer in general. I introduced UDP. UDP is a very simple connectionless packet-oriented transport protocol, which really just adds ports to what the underlying layer, the IP layer provides, which is the ability to send a packet from one place to another. But in order to support streams of data and more data than you can fit in a single packet, you need to break up data into segments and include and handle delivery confirmation and ordering. And this is done by sending acknowledgement packets back from the receiver to the sender, positive acknowledgements. And we introduced the concept of a timeout, which is used by the sender to realize that a packet was never received. And when a timeout happens, the sender resends the packet. And that's how things eventually get from the sender to the receiver, even though the transmission is unreliable. That's like the general idea. And we moved from the simplest naive scenario where you use the stop and wait protocol, where you send one packet, wait for the response, and move on to the next one. That worked, but it was really slow, so we looked at different ways to parallelize or pipeline the packet transmissions. When we do that, we need some kind of window size to dictate how many packets are allowed to be in flight, because we don't want to overwhelm the network, and we don't want the sender or the receiver to have to remember an infinite amount of state. It has to be finite, and the window size determines that, and also controls basically the amount of throughput. That's the amount of data that you can have from the network at any given time. And we talked about go back N and select and repeat, which are two different pipelining protocols. And go back N was maybe simpler. It used cumulative acknowledgements. Select and repeat was a little more efficient because it had introduced an additional timer for every packet that is on that is in flight in the network. So it's more complex, but it avoids unnecessary repetition in retransmitted packets. So somehow it's more efficient, right? And I showed you some demos of those, and you can try out those demos on your own as well. Okay. Any questions about that before I move on? Okay. So TCP is reliable transport, like I've talked about in the last lecture, but it's the practical, real-world implementation of reliable transport that's evolved from the 1970s through today. So TCP is what's used on the internet for the vast majority of traffic. UDP is not very common, in fact, because usually you have a lot of data to transfer, not just small bits that can fit inside of a UDP packet. It uses positive acknowledgements, like the go back N and select and repeat protocols, but it combines ideas from both go back N and select and repeat, as you'll see. It also has this additional feature that it manages connection pacing, meaning the rate at which you send packets, and this is called flow and congestion control. We'll see in the second half of this lecture what that's about and why you need it. And one difference between TCP and UDP, we talk a lot about the advantages of TCP. You know, it allows you to send lots of data. It allows transmission to be reliable. I mean, transmission is not reliable, but in the end, in the application layer, it looks reliable because you have retransmission and delivery confirmations. That's all good stuff. One of the big disadvantages of TCP compared to UDP is that you need to set up a connection beforehand with what's called a three-way handshake, so there's a delay before you're able to start sending the first bit of data. And that handshake involves exchanging initial sequence numbers for both directions of the connection, so we don't start off with sequence number 1, and we'll see why later. We actually choose a random initial sequence number for both directions of the connection, We do that for two reasons. First of all, so that if we always start off sequence numbers at like 0 or 1, then it would be very easy to confuse packets from a different connection, specifically from an old connection between those two computers. If the packet is delayed from the previous connection and it comes in and has sequence number 3 or 2, some low number that's likely to be reused, then you might take that data and insert it into the new connection's data stream, which would be a problem, right? Because the data is totally unrelated from the previous connection. Having a random initial sequence number eliminates that threat, because your previous conversation might have been using sequence number 3000, and then the new, so there's you expect to see 3000, 3001, 3002. The new connection uses a totally different sequence number, like let's say 17,000, and if you see something like 3001 come in, you can just ignore that because that's way outside the range of expected sequence numbers you would expect to see for that new connection. Okay? So it protects against old packets being confused for the packet in the new stream, and also makes it harder for attackers to inject fake packets into your data stream, because they have to have observed other packets to know what range sequence numbers you're using. Okay, although it's not really a strong security mechanism, it's just a very weak type of security mechanism. Okay, so here's what the TCP packet looks like. I think I showed a similar diagram for UDP last time, and the UDP one was really pretty simple, and this one's a lot more complicated. There are a lot more fields, so every single TCP packet you send has all of these headers in there. There's a source port number, a destination port number, same as UDP. This is to distinguish between different connections on that computer. There's a sequence number, which indicates, in what place in the stream this data fits, right? Is it the beginning of the stream, somewhere in the middle, so on. This is used to reorder the data when it arrives, as we know. One big difference here is that this is actually counted by bytes instead of by the number of segments. So this doesn't go like 1, 2, 3, 4. It goes like 0, then 1024, then maybe 1200, depending on how much data you've sent. The acknowledgement numbers, there's actually an acknowledgement number and a sequence number in every single packet, because acknowledgements are actually piggybacked on data that's sent back in the opposite direction. We'll see that in a second, I guess. So let me not jump ahead of myself. But if you're sending an acknowledgement back, you put the acknowledgement number in this field. And there are some other, there's a bit field here where the bits here have different meanings, which will make more sense later. And there's a receive window here, which indicates to the person on the other end how much data you're willing to receive. So if this says, for example, 3000, it means that the person on the other end who receives this packet should not send you more than 3000 bytes. Okay, that's used for flow control, which we'll see later. There's also a section here that's variable length. There are other options you can communicate about the TCP connection, which are more advanced and less fundamental, which we're not really going to talk about. But this part of the header is always there. Okay. Yeah.
For some reason, you decided to change the size of the window, so the receiver.
Yeah.
Established that in the first connection, right? So the client.
Yeah. So this does change, and that's why this is part of every single packet that gets sent back and forth. So initially, you might say, okay, I'm ready to receive 3000 bytes. And then the next time you send a packet, you might say, now I can only receive 2000 because I filled up part of that buffer, or maybe I made more space available in my buffers. I have more space available there. So that's something that changes over time, and just it allows each end of the connection to advertise at that given time how much space they have in their buffer to receive more data. Yes.
So is the sequence number there like generated by first getting a random number and then adding however many bytes are coming in like per packet?
Yeah, so in the initial handshake, it's random, and then as you send packets, you keep adding the number of bytes that you've sent. Well, there's an example that will show that. Okay, so different than the examples we saw last week. So last week we showed like data packets and then acknowledgement packets coming back. And those acknowledgements we assumed were just like very short packets that said, I acknowledge this data. But in reality, TCP is more clever than that. It assumes that you're sending data. It allows you to send data in two directions. And by having an acknowledgement number built into this header field, it allows the receiver of data to acknowledge data it received in the next bit of data it sends in the other direction. So acknowledgments are sort of piggyback from data flowing in the opposite direction. If that makes sense. Maybe we'll see some examples of that here. Okay, so here is a picture showing a packet of data and an acknowledgement. Okay. So like I said before, sequence numbers in TCP don't count packets, they count the number of bytes in the byte stream. And so at this point, this diagram here, using the same diagrams we showed last time, this indicates that the sender has some amount of data in flight here that hasn't been acknowledged yet. All this data has been acknowledged. This is in flight. This is the next bit of data it's sending. And so the sequence number here indicates the offset from the beginning, the number of bytes from the beginning of the connection that get to this point, right? And the size of the segments can be different depending on the needs of the application. The application may just send a little bit of data and then a lot of data. If it's sending a little bit of data, it may create a segment that has just a few bytes here, and therefore like the difference in sequence numbers may be small between some of these, or it could be large up to the maximum segment size, which is usually about 1.5 kilobytes, like 1,500 bytes. Okay. So this goes out with the data here and a sequence number in here, and a packet flowing back to the receiver. Sorry, the arrows are really faint. This is going in this direction. This is going in that direction. Would have an acknowledgement number in this acknowledgement field. It would also have the acknowledgement bit set in this bit field I showed you before. So sometimes this field is used and sometimes it isn't. If it is being used for an acknowledgement number, you have to set this bit. And then the receiver would know that this acknowledgement number should be used to acknowledge one of the in-flight packets and know that it's no longer in flight, it's been received. Okay. So similar to go back N, acknowledgements are cumulative in TCP. So when the sender says it acknowledges a certain number, it acknowledges everything up to that number. But different than go back N, TCP allows and expects the receiver to keep out-of-order packets, like early packets, in a buffer and reorder them when the late packets arrive. Right? But it doesn't really have to. So the receiver can drop out-of-order packets, or it can buffer them for later reassembly, like selected repeat. So here's an example of TCP exchange. So we'll talk about the handshake later. Let's assume the handshake has already happened. After the handshake, there are random initial sequence numbers here. So 42 for the client and 79 for the server were decided. The client sends a GET request. So here's the body of the request, which looks familiar to you by now. And this is put inside of a TCP segment. And that segment has sequence number 42. And the acknowledgement number is 79 because this 79 was during the handshake, both sides learned of the other side's sequence number and told the other side of their own sequence number. So at this point, basically, what this part of the message means is that I'm sending you data that starts at position 42. It's 42 not 0 because it's a random start, and the receiver will know that 42 actually is the start. And I'm acknowledging that I've received everything up to 79, which is nothing actually, because 79 equals the beginning number. Okay? When the server gets this message, it will parse it, and if this is a web server, right? When you get a request, you don't just say, okay, I got the request. usually you want to send the data that corresponds to the request back. Like you want to send the HTTP response back. So the server might construct an HTTP 200 OK message that has some data. All right, so let's say there's 1,200 bytes of HTML that's being returned, and it fits into one segment. So the body will have that data, and then you're going to have some TCP headers on top of that. The TCP headers in this case are going to have sequence number of 79, because this is the beginning of the data stream in this direction. Right? So it's starting at the beginning for the web server. And acknowledgement number is 142, because this request happened to be 100 bytes long. Forgot to say that. So if this GET request was 100 bytes long, it's saying that I'm sending you something that starts at the beginning of my data stream, and I'm acknowledging that I've received everything up to 142, which is 100 bytes past the beginning of the sender side. Okay. And at that point, that's the end of the HTTP transaction, right? This short request goes in, and then a short response comes back. We don't have to. In this case, we're not worrying about multiple packets because we're talking about small amounts of data. Right, so just one packet in one direction, one packet back. The client gets it, and the client actually has everything it needs, but it still has to send a packet back acknowledging that it received this data. So it sends back an acknowledgement message with no data, no body. So the sequence number it sends for itself is 142, saying the data I'm sending you begins at position 142 because I've already sent you 100 bytes of data. We started at 42. I'm acknowledging that I received everything on your end up to 1279, because that's what you get when you take the 79 that we started with and you add the 1200 that I received, and I'm sending you 100 bytes of data. So the server gets this. It sees that the sequence number plus the data it received is 142, which it already has acknowledged before. So previously it acknowledged 142. So it doesn't need to acknowledge anything further. And the transaction is done. Yeah?
Does the acknowledged message have no size?
In this case, it has no size because the client had no data to send.
Oh, no, okay. So it's
Yeah.
just
If this application decided to send more data back, like let's say it had to fetch an image or whatever, then there might be some data here, in which case the receiver, the server that receives it, would take the size of that data and add it to the sequence number and see that it needs to acknowledge now some later point in the stream. So it would send an acknowledgement back in that case because there was new data that came in. But since there isn't, there are no further acknowledgements. Yes?
I guess building on that, if the sender were to send more data, that would not have a sequence number 142. It would be something bigger because it already sent this last packet.
I think that actually the sequence number that is used, the sequence number that's used indicates where the beginning of your data fits in. So it'd still be 140. Like you notice that this one starts off with 42, which was the initial sequence number, and in here there's also a length field. I think it might be part of the IP header, but anyway, this has 100 bytes, and it begins at 42, and so the receiver does the math of 100 plus 42 to get
It's
the
counting the length of the data sent, not the length of the total packet sent.
It's the length of the data in the current message.
Does the server have to keep in a buffer or somewhere all the acknowledgements that it sent?
It doesn't have to keep all the acknowledgements, it just has to keep the highest acknowledgement it has sent. Because it uses cumulative acknowledgements. It'll only acknowledge, so that this is different than selective repeat. Selective repeat, it has to kind of keep track of everything that it acknowledged. So the acknowledgements tracked by the receiver are pretty simple. It just has to keep track of what's the highest acknowledgement number I sent back. In this case, it was 142 previously. And if I get more data that fits in like right after 142, then I can acknowledge it with a higher number. But if I get data that is out of order, that's early basically, and there's a gap, then I don't acknowledge anything. Actually, well, I do acknowledge the old number again, and the receiver, we'll see what happens with packet loss in the next slide. maybe not the next one, but in a few slides. Okay, so we talked about timeouts previously as being necessary to retransmit packets, right? It's the only way for you to know that something is lost. You never really know that a packet is lost, but at some point you need to assume it was lost because a lot of time elapsed. You can't observe the network. The network doesn't tell you something was lost because that's just the way that that this type of packet networks, the internet, is designed. So TCP keeps one timer, which is for the oldest unacknowledged segment, and it retransmits that one segment when the timer expires. When an acknowledgement is received, it starts the timer again for the next lowest unacknowledged segment, if any. So if you get a new acknowledgement saying that more data was received, then you can start a new timer for that next bit of data that hasn't been acknowledged yet. And you can kind of see that the timer has to be set carefully. You can't just choose an arbitrary value. If it's too long, then you waste a lot of time before a necessary retransmission. You don't want to wait like 3 days before you decide, oh, this packet's lost. If you know the network is probably going to only take a second at most. But if it's too short, that's also a problem because you might decide too early that a packet is lost when actually you're eventually going to get a response. And you can send a lot of duplicates unnecessarily. That puts a lot of extra load on the network and kind of confuses everyone. So you need to somehow figure out an ideal value of the timer. But this is kind of difficult because different networks have different behaviors, right? I showed you before that if you're communicating from here to Argonne National Labs nearby, the round trip time might be like 20 milliseconds. If you're communicating with a server in China, the round trip time might be 10 times or 20 times longer, 400 milliseconds, half a second. So, so you'd want to give up quicker if you're communicating nearby, but you want to wait longer before you give up if you're communicating further away, right? So how do we set this value? How do we set an ideal value of the timer? In other words, how do we know when to give up and try again? What do you guys think?
So you just keep the first time you receive the first package when handshaking, and you can use that time as a reference.
Yes, you kind of remember the last time that you got a packet back. How long did it take? Because there's some handshake initially, definitely, and that involves back and forth. And throughout the communication, there's always there are acknowledgments being sent back for every message that was sent. Or not, well, usually, but and that tells you how long you should expect the packet sent. So you know what the round trip time should be, or you have some history of what the round trip times were, and you can use that as an estimate, sort of, right? But it's more complicated than just that because it can vary. So yes, the answer is that TCP should keep track of recent round trip times. So constantly measure the delay between every transmission and the acknowledgement, and somehow use that history of round trip times to decide the timer. Okay. But there's a little bit of nuance in how to actually calculate it specifically. Okay. You don't want to just use the previous delay because if it's a little bit longer, then you expect it to sometimes be a little longer, sometimes a little shorter. So there's variation. The network doesn't behave constantly. Like here's an example of some observations made by the authors of our book, where the yellow line indicates the round trip time for subsequent packets, right? And you see that it kind of varies between 190 and up to 320 milliseconds. This is across the Atlantic Ocean. But it's kind of always within this range, right? So what's done in a really simple way to compute like an average of something that varies like this is to use an exponentially weighted moving average. And the reason that's nice is because you only have to remember one thing. You don't have to remember all the history. You don't have to remember all these points. You just remember your previous estimate. So you have some previous estimate of the round trip time here. And when you get a new sample, you average it. So I've just observed that the round trip time was 400 milliseconds. Previously, I thought it was around 200. And so my new estimate should be somehow between the two. It should be a little higher because my new observation is higher than the old average. But it should still take into account the old information because I know that my new one is just one sample, and that previous estimate is based on many samples. Right? So all it is it's a weighted average. So you give some, so this alpha and 1 minus alpha add up to 1. And if you choose an alpha, like for example, if you choose alpha to be 1/8, which is 0.125, then what that means is that you take one of your current samples and you take 7 of your previous samples and you average them together. And that gives you something that changes slightly every time, but takes into account a lot of the previous history. Okay? And you just have to remember one thing, the current estimate. Okay? So it gives you a smooth average, and that smooth average changes over time. And this green line is the moving average using this formula of the round trip time. So like here, for example, your current estimate was this, but then you got this sample here, which is higher, so you move up the next time. Or you got this one, and then you move up the next time. Then the next one you got was lower, so you move down slightly. And it kind of is it's a smooth moving average that changes when new data comes in, but still uses old data to an extent. Okay. And another point is, so you want to set the timeout to be greater than your current estimated round trip time. Like you don't want the timeout to be exactly your estimate, because then half the time the observation will be greater than the estimate, half the time the observation will be lower than the estimate. That's what an average is. Like half the time you expect it to be greater, half the time you expect it to be lower. You don't want half the time to have a premature timeout. So you need some safety margin. So that most of the time your timeout is set high enough that you rarely ever get a premature timeout. Okay. So how do you calculate that? You really need to know the deviation of your round trip time to decide how much safety margin you need, right? So like in this example, if it was varying by this amount, by a large amount, then you need a safety margin that's pretty large to not get premature timeouts. If the variation is very small, then you need only a small variation, right? So these two colors of observations of round trip times represent two different scenarios where the average is the same, but the variation is different, deviation is different. So this blue connection has a very consistent round trip time. It's always pretty close to 200. But this pink or red one has more variation in the round trip time, right? So for this blue one, if you're observing this connection, you actually could set the timeout to be just greater than 200. Like if you set it to 210, you would be okay. Like you would never have premature timeouts. But for this purple, this square pink one, you would want to set it higher because there's more variation. So maybe a threshold of 250 or 260 would be a good one. Okay. So you start off with a timeout and then add a safety margin that is proportional to the variation that you expect. And so, and the next question is, how do you actually choose or calculate that variation? Well, you do it just in exactly the same way that we calculated the round trip time. You calculate a moving average of the deviation. Okay? So your current estimate of the deviation is based on your previous estimate plus your latest sample. So what do I mean by sample? So you take your current round trip time and you calculate the difference with what your estimate was, and that tells you what the deviation was for this last step. Right? So, for example, in this picture here, you see what the estimated round trip time is. So here, at this point in time, when you observe this round trip time, you take this difference here, and that tells you what your latest deviation was, and that factors into the moving average of deviations over time. So this is what this deviation was, the previous deviation was this, the previous deviation was that, the previous one was that, and so on, right? So you take a moving average of those deviations. Okay? And as a rule of thumb, the constant factor is a little bit different for the deviation, but it's not too important. So then to finally calculate the timeout, you take your estimated round trip time, which was the moving average, and you add on top of it a factor of the deviation of your estimate of the deviation. In this case, like a lot of implementations use a factor of 4 just to have a relatively high margin of safety so that you prevent premature timeouts. Okay. But exactly how this behaves is up to the implementation of TCP. There are RFCs that make recommendations, but different implementations can make different choices if they think that they can improve upon the performance by making different decisions. And right off the bat, we don't know much about the connection. You do have the handshake, which gives you a little bit of information. But even the handshake needs a timeout. So initially, you set the timeout to 1 second until you get some information. Okay. So here is a simulation, I guess, of different observed round trip times in these pink circles. And the green line shows what the timeout would be, or how the timeout would evolve over time. And these dotted lines are the estimated round trip time up here, and the estimated deviation of round trip time here. So these are the moving averages. And you see that initially the timeout is set to 1 second. Then once you have some data, you can start setting it to this moving average of the round trip times plus 4 times the moving average of the deviation. So if you take this line and kind of stick on top of it, you get the green one. And you can see how it evolves to react to the network conditions changing. Right? So this simulation involves 3 different scenarios. First off, the network was slow, or actually was fast. The delay was short, and there was a moderate amount of deviation. Later on, the network got slower, the latencies were longer, and there was a lot of deviation. And so in that case, we wanted to have a really high timeout, and you can see how it adapted. And then later on, it got more consistent, but was still on average the same delay. And when it got more consistent, the timeout that was used ends up getting smaller because less safety margin is needed. Right? That's all a consequence of these simple formulas. Okay. Questions about that? Okay.
Wait,
Yes.
sorry. What was the dev round trip time there?
What's this here?
What's the dotted gray line?
Dotted gray line is the moving average of the deviation in round trip time. So the way this is calculated is you take your current, so basically it's a moving average of the difference between these purple dots and the blue line, which is the moving average. So initially, they vary within a kind of a small range, and so we have a relatively small value. Later on, they vary quite a lot, and therefore this estimate is higher, the estimate of the deviation. So this is showing how much variation there is in the delays, the latencies. Later on, they become more consistent, so the value drops down again. And this is used to influence the margin of safety, which is the amount that the round trip time is put above the estimate of the timeout. I seem to be bleeding my own blood. It's weird. Right back.
Wait, what happened? You need to play
All right, so that's a pretty simple concept. All right, so timeouts are used to decide when to retransmit, right? Here's a simple scenario where you send a packet, the receiver sends an acknowledgement, but the acknowledgement's lost. Eventually there's a timeout, and then the sender retransmits. When it retransmits, it uses the sequence number of the lowest unacknowledged. The last acknowledgement it got back becomes the bit of data that it sends back, and eventually it's acknowledged. And again, the acknowledgement number that's sent back is equal to the sequence number it received plus the amount of data that was in that packet. So it's 8 plus 92 is 100. Yeah. So in this scenario, there's a premature timeout. So the data was, nothing is lost on the network, but the acknowledgement doesn't get back fast enough for the sender to make the sender happy. The sender panics, I guess. The timeout expires, and it resends the data, the lowest data that hasn't been acknowledged, which is 92 in this case. It only sends one packet, actually. That's the way TCP works. It only sends one segment when there's a timer expiration. But it eventually does get these acknowledgments, and it increments, send to base in this case means the offset of the next data it's going to send, the sequence number basically the next data it will send. At this point, it finally realizes that 100 was acknowledged, so it can start sending the data after 100. And then later, 120 was acknowledged, so it can start sending the data after 120. And what's shown here is that, so this packet here was that kind of early panicky retransmission, the unnecessary retransmission. When this is received here, the receiver already got this data before, and it knows that it's acknowledged past that. So to react to this, it sends the acknowledgement back, but because it's using cumulative acknowledgements, TCP uses cumulative acknowledgements, it can't send the acknowledgement. If it sends acknowledgement of 100, that would confuse the sender, because it would make the sender think that it has not seen anything past 100. So it actually sends acknowledgement of 120, which is the later data it received here. Just to kind of clarify to the receiver exactly how much data it's received. Okay. This other loss scenario involves an acknowledgement that's lost. So the first acknowledgement is lost. And in this case, because cumulative acknowledgements are used, there's no problem at all. Actually, this loss causes no change, no delay, and no change in the sender receiver. Because the second acknowledgement, fortunately, does come through, and that carries this 120 number, which is greater than 100, and this kind of overrules. This tells the sender that the receiver received everything up to 120. If this first packet was lost, then the sender would not have sent 120, it would have sent 92, this acknowledgement. Okay. And then it can continue sending the next bit of data after 120, right? So, these are the rules for acknowledgement generation in TCP. And I guess we'll see how these work in some examples later. But these are kind of here for reference. So when the receiver gets an in-order segment with an expected sequence number, so this is a normal scenario. It's already gotten everything up to a certain point. It gets the next bit of data. Then you'd expect it to send an acknowledgement back. It actually doesn't in that case. There's this behavior called delayed acknowledgement. This means that you don't immediately acknowledge data. You wait a little while, up to half a second, because you don't want to send a packet that has just an acknowledgement. You don't want to send just a small packet that says, "Okay, I got this." You want to wait until you either have a response ready to send back, or you get more data. So typically, what happens, like in this scenario here with the HTTP request, so remember TCP is handled by the operating system below the application layer. Like in your programs that you wrote for Project 1, you didn't have to do anything with TCP. That was all managed by the OS. Well, the OS got this packet with the request. It could have sent an acknowledgement immediately before your program even had a chance to process it, before you had time to open the file and generate the data. But that would be wasteful, actually, because eventually it's going to send data back, and you might as well piggyback the acknowledgement on top of the response. So the OS waits for half a second before sending an acknowledgement. Now, it turns out that your program can pretty quickly open the file and generate this response, within, let's say, 50 milliseconds or 20 milliseconds. And well, I found the source of the blood. Glad to know that. Yeah. So, yeah. So then 20 milliseconds later, your application calls the send method, the send function in your TCP library to send data back. And at that point, the OS will send the data back, and it will use the proper acknowledgement number that acknowledges the data that was received before. Right. So this delayed acknowledgement is designed to with the knowing that applications typically send data back when they get data. So don't send an acknowledgement back. Wait for the data that's going back before you include the acknowledgement. But if that doesn't happen, so that's the second case. If you receive an in-order segment, so nothing was lost, but you get yet another bit of data with an expected sequence number, but there's a segment that you've received that you haven't acknowledged yet. In that case, so in other words, the previous acknowledgement was delayed. In that case, you send immediately a cumulative acknowledgement acknowledging both those packets. So if the sender basically beats you to sending the next bit of data, you send an acknowledgement back that acknowledges both the previous packet and the one you just got. And that's to prevent unnecessary delays. And the other scenario is when you receive an out-of-order segment, which usually occurs because there's a packet loss. So you basically receive a segment that has a really high sequence number, higher than you expect, or maybe just slightly higher than you expect. So there's a gap detected in the data stream. In that case, the receiver should send back a duplicate acknowledgement immediately. By duplicate acknowledgement, it's called a duplicate acknowledgement because it's an acknowledgement with a low acknowledgement number that you already sent previously, which indicates the sequence number of the next expected byte, basically that gap that you haven't received yet. The beginning of that gap will be in the acknowledgement that you send back, and that acknowledgement number was already sent back previously, which is why it's a duplicate acknowledgement. And then if you receive when you receive a segment that fills in a gap, then you can immediately send back an acknowledgement. If that packet is at the beginning of the gap, so in other words, if you're able to send a higher acknowledgement than you previously sent, basically. Questions? So yet another. So there are a lot of little. So these rules could have been different, but these were decided. These changed over time, and they've come to be what they are based on taking into account the kinds of losses, the kinds of behaviors that typically happen on the network, and the kinds of behaviors that applications typically have. Yes, questions?
So if they get a segment that fills in the gap partially but doesn't start at the gap, it waits for another segment?
Yeah, it just you expect it to store that segment in a buffer, and doesn't send anything back, just waits for hopefully that gap to be filled in.
What if it receives from the start of the gap and not it creates another gap? You know what I mean?
Well, okay, so if you're talking about, so when we say gap, we mean like this data has been received, somehow some data was received out of order, like later data was received, and there's a gap here, right? And in the case when if this here is saying that if the segment was here, that you received was here, then great, you can just acknowledge up to here. So previously you acknowledged up to here, you can acknowledge a little later. That's kind of obvious. Then the scenario you were asking about was if it creates another gap, like if it's here, it creates two gaps.
Yeah.
Whether it's here or it's here doesn't really matter. It does the same thing in both cases. It's stored by the receiver, probably. It doesn't have to be. The receiver will probably store it, and it won't send anything back. It hopes to later fill in these gaps, and it basically hopes to at some point advance this acknowledgement number, this point where it knows it's received everything up to this point, because this data can be sent to the application, because it's all in sequence. This is data, it's ready to go. All the stuff here, it hasn't been able to reassemble. It hopes that it'll eventually receive this. If it never receives this, then eventually the client, the sender will time out eventually and retransmit it, and hopefully it does. So it will eventually be retransmitted, and so it should eventually be received and acknowledged. Does that answer your question?
Yeah, so none of the later out of sequence packets resets the timeout.
Well, the timeout is all on the sender side, not the receiver side.
Oh,
So the sender's timeout starts when it sends a sends a packet that's at the beginning of the list that hasn't been acknowledged. So if it's received, the sender has, assuming the sender has received this acknowledgement, it's sent many packets after that point, those that are all in flight. The timer it has corresponds to the first packet that wasn't acknowledged. When these other ones get acknowledged, those don't change the timer. Only when this one is received, the acknowledgement is received for that one, does it change the timer. So the receiver, the sender is waiting for this one to be acknowledged. And if it isn't acknowledged, it'll retransmit.
There's no negative acknowledgements.
No, there are no negative acknowledgements. I mean, the receiver does know, like, hey, I'm missing certain data. Like, maybe you should send some of this to me. Like, you might design a protocol that would have negative acknowledgements, but it doesn't exist in TCP. You just assume that the receiver is tracking a timer for anything that hasn't been, the first one that hasn't been acknowledged, and you know that's eventually going to expire. All right, so fast retransmission is a little optimization to TCP. It was added in the 90s, I think, in TCP Reno, which is the name of an implementation of TCP. And in this case, it allows retransmissions to occur before a timeout happens, only when three duplicate acknowledgements are received. So this scenario shows four packets in flight, well, 5 in flight. The second one is lost, and that causes this. Sorry, whoa. That causes the receiver. When the receiver gets the first packet, great. It sends back an acknowledgement of 100 because it's 92 plus 8. The second one never arrives, and the third one arrives out of order. It sends back an acknowledgement. I think that's what we said here. Arrival of out of order segment, immediately send back a duplicate ACK. So for this one, which it's out of order because the one before it wasn't received, it sends back a duplicate ACK, same acknowledgement, 100. Same thing for the next out of order one, the next out of order one. So these are ones that are in a gap. Well, they're not in a gap, but they go after the gap that already was received. The receiver, when it gets this third duplicate acknowledgement here, this is an expected acknowledgement. This is a duplicate. This is the second duplicate, third duplicate. It immediately resends the lowest unacknowledged segment. So it sends this 100 packet again at that point. And the reason it does this is because it knows, the sender knows that packets are getting through. So the issue is not an issue of delay. It knows that it should have gotten that acknowledgement back because it got acknowledgements for later packets. And so in fact, it got many acknowledgements for later packets, meaning that the confidence that we're pretty confident that that one should have been received. Therefore, they must have been lost somehow, right? So let's retransmit. And so at this point, it resends this packet with sequence number 100 corresponding to the triple acknowledgement, triple duplicate acknowledgement, which is a duplicate of this message here. Okay. Even though the timer hasn't expired. All right. So, in summary, TCP has characteristics of both of the policies I talked about last time, both go back in and selective repeat. So, like go back in, it has one timer. But unlike go back n, it resends just one segment when that timer expires. Just the segment corresponding to the latest received acknowledgement. go back N, like go back N, it has cumulative acknowledgements, so the receiver can send an acknowledgement that acknowledges many packets, but unlike go back N, the receiver can save out of order packets and reassemble them later. Right, that's a feature of select and repeat. That's pretty nice. And like go back N, a duplicate acknowledgement is sent back if there's an early segment. So this behavior of sending back an acknowledgement with a duplicate number from a number you previously sent, that's also in go back N. Yeah. So the new features that we haven't talked about that are not present in either go back N or select repeat are these guidelines I mentioned for setting the timeout interval. That's all new. Delayed acknowledgements, where you wait a little while before sending back an acknowledgement, hoping that the application will have some new data to write back. And then the fast retransmit after the triple duplicate acknowledgements, that's new. Those are both optimizations based on like real world experience. And there's connection set up with three-way handshake. There's also a three-way teardown handshake, I guess you could call it, which we'll talk about next. And there's also a window size that is set dynamically to implement flow control, congestion control, which we'll talk about later as well. So these two points are coming up next. All right. Okay, so the TCP window. Let's revisit this in more detail. We already said before that the window decides how many segments or packets can be in flight for this connection. And previously we said that the reason for this was not to overload the network, not to overload the receiver's buffer with too much data, and so that both the sender and the receiver don't have to remember like an infinite amount of data. Just to limit that. Okay. So notice that the peak throughput is proportional to the window size. So assuming that the round trip time is constant, then the amount of data you send over time depends on the amount of data you can have out in flight at a given time. Right. So remember that there was that example last lecture with the fast connection between New Jersey and California. When you were doing stop and wait, the throughput was terrible because there's only one packet in flight, and you kind of multiply that by the round trip time to get the total amount of data, or divided it. If you could put more packets on the wire in flight, then you get much higher throughput. So we've seen these pictures before with the window size, and the packets that have already been acknowledged and have been handed to the application layer come before the window. Inside the window, the ones at the left side are the ones that are in flight. And then these, you might have some packets that have not yet been sent, or some data in the stream that hasn't been sent yet that could be sent because the window allows more data to be sent, but you just haven't sent it yet. That's the yellow bit. And the reason for this could be that the application just isn't yet ready to write more data. Therefore, you have some space available in the window. And so to look at this on like the network, in a simple network diagram, where the sender is sending to the receiver, the data that's already been acknowledged is here. So so the packets go out and acknowledgements come back. When an acknowledgement comes back, that becomes part of the data that's already been acknowledged here. And then the data that's in flight is both flowing toward the receiver, it's queued on the receiver, it's being processed by the receiver, and it includes acknowledgements that are being processed by the receiver and acknowledgements that are in flight back to the sender. So all these are like 3 or 4 different stages here that a segment could be in and still be kind of in flight from the sender's perspective. Because all the sender sees is these 2 wires. The sender doesn't really see all the details of what's going on. Okay. So by controlling the window size here, the number of packets out on the wire, the sender can prevent overflow of the receiver's buffer. So there's some buffer here that the operating system and the networking hardware both have to store packets that haven't been delivered to applications yet. And there's also, the network itself has routers, which we're not showing, that are like hops along the way, that have limited storage capacity. Having a window too large could both overload the receiver and cause losses here, and it could also overload the network and cause losses here. The losses here, preventing the losses here is called flow control. So this is preventing overflow of the receiver's receive buffer. It's flow control. And preventing overflow of the queues in the routers and losses in the network, that's congestion control. So congestion relates to the network, and flow control relates to the receivers. Okay. So there are two different sets of policies for controlling the same thing, the window size, that affects two different types of losses. Two different problems you're trying to prevent, I guess. But they're related problems. They're both buffer overflows. But they're two very different policies involved. And the reason that there are different solutions is because you have different levels of feedback available from the receiver versus from the network. Basically, these network devices, the routers don't tell the receiver the sender anything, whereas the receiver can actually provide information back to the sender about its own state. So every packet has a receive window in the TCP headers, which allows the host to tell the other side how much space it has available to receive more data. And this is a very simple mechanism to prevent overflow of the receive buffer because the sender will stop sending data when it has more data in flight than the receive window indicates. Yes?
Is that very explicitly like space left in memory, or is it more of a suggested thing based upon?
It won't be space left in memory. It'll be much smaller than that generally. It'll be space left in the memory that's dedicated to processing and queuing incoming packets. And it could also be set. It could be a buffer in not RAM, but the network cards hardware. There could be memory on the network card that is dedicated to buffering these incoming packets, and that can be monitored by the operating system and reported in the receive window. It depends on the hardware, like how much buffering is in the network card versus in the actual machine itself, machine's memory. But you wouldn't expect this to be huge. These days you have machines with many gigabytes of memory. You wouldn't probably see my laptop has 16 gigs of memory. This wouldn't report 10 gigs. It would be some smaller number. But and I don't remember exactly. This is 16 bits, right? So I think there's a multiple that's applied to this because it can be definitely is more than 64 kilobytes, and that multiple is either a constant that is necessary ahead of time or it's stored in the options. I don't remember exactly. Yeah.
Similar question before. So the bytes that it can receive, that's referring to payload or entire packet size?
I think this is just the payload.
Payload, okay.
And it's not.
So in reality, the buffer is bigger because it would have to receive the headers and all the other stuff too.
Yeah, so you might have to set it conservatively so that the sender doesn't overload you with headers. It's hard to know ahead of time because it doesn't reflect the total size. Then depending on how the sender chunks up its data, there could be more overhead or less overhead. If there's smaller packets, there'll be more overhead. So it's not precise, I guess. So there's a little bit of inaccuracy or wiggle room that you need to add. Okay. All right. So congestion control, like I said, is also about having senders limit the amount of data in flight, but it's much more complex to solve because there are many routers along the path that a packet takes to reach its destination, and those routers are not all communicating back from the sender, and they're handling many different connections at the same time, and the overlap of those flows on the routers will affect what's dropped and what isn't, and how much space is available. So it's much harder to solve, and there's no such explicit feedback back from the routers to the sender telling it how much data to send. So what we'll see later on is that the way that the congestion control window is decided is based on observations, and just like when a packet is lost, then that means that the network is congested somewhere, and so we need to react. It's reactive instead of proactive. So let's come back to TCP connection setup, which I alluded to earlier. This is, before data can be exchanged, the two hosts involved have to agree on a few parameters. There are two obvious parameters, and there are some other parameters they can set too, but most importantly, they need to set their initial sequence numbers in both directions. And you saw why, because we use random sequence numbers. They need to set the receive window size for flow control, which we just talked about. And so if you don't hear anything back from the other side, you can't start sending data without getting this information first. That's all I'm saying, right? So the handshake exchanges this information. And again, we have a random initial sequence numbers, both so that packets in this connection are not confused with packets from prior connections, and also so an attacker can't easily inject fake packets into your data stream. But in general, both of these relate to making sure that packets have numbers on them that uniquely assign them to one connection with a very low probability of another packet being accidentally interpreted as being part of the current connection. Okay, so in order to exchange this information, we use a three-way handshake, which means one packet is sent back, and another packet is sent. That's the three-way handshake. So it's like, the first one is called syn, meaning synchronize, and you'll notice back in the diagram I had for the headers, there were bits. There are bits here so this S, if this S bit is set, this is syn. This means it's a syn packet. So when I say you send a syn packet, it just means you send a packet that has a 1 in this position, and then you include your sequence number here and your receive window here. You set this bit, and that kind of that's your first packet in the handshake. Sorry. And then the receiver sends back a syn ACK packet, which acknowledges the fact that that first syn was received, and also includes its own parameters, the initial sequence number and the window size for its end of the connection, and then the initiator acknowledges back that it received the syn ACK. Okay, so even though no data is exchanged, you kind of increment the sequence number by 1 to acknowledge for these acknowledgements here. So like this one here sets an initial sequence number. The syn ACK that comes back has an acknowledgement that's this initial sequence number plus 1, and then the third acknowledgement that is the second acknowledgement here in the third packet is the sequence number that the second one chooses for itself randomly plus 1. Okay. Even though 1 byte of data wasn't really sent, that 1 byte kind of represents the handshake information. So here's an example. These pictures are from the TCP IP Illustrated book, which is a good reference if you want to. Then I'll turn it to what's in the other textbook. It's a little more low level. It has more examples. So this syntax here means that this packet has a syn bit set. The sequence number is this number, this big random number. The end of the data is here. That's not part of the header, but it's just based on taking the data size, which is 0, and adding that to the initial sequence number. MSS means maximum segment size. I'm not even sure why it's included. The maximum size of the packet. The response back is another random sequence number, this 182 whatever. That's the sequence number that the receiver chose. And it also acknowledges the sequence number that was received plus 1, so it goes from 21 to 22. And then the initiator acknowledges the sequence number that was chosen by the other side by taking that number, adding 1 to it, making it 22, and sending it back in the other direction. So in kind of a more abstract form, you send the syn packet with sequence number j, you send back acknowledgement of j plus 1 and your own sequence number k, and the first party sends back acknowledgement of k plus 1. Okay. So when you're dealing with TCP sockets, you either can open a socket actively or passively. And actually, you did both in project 1. An active socket is when you actually specify the connection partner, meaning you specify what host you want to connect to. That's like when you implemented the client. When you did that, you said, okay, I'm connecting to this remote host at this port, and in that case, you're actually initiating this SYN handshake. So immediately when you start when you open up that packet in your client code, you're sending a SYN to the other side, and the server is just kind of listening. The server didn't do anything. You're the first actor. You actively open the socket. When you implement the server, you create a listen socket, which is a passive socket, which doesn't send anything at first. It just listens, and it hopes. So you're on this side as a server, and you're hoping that eventually someone's going to send you a SYN packet. So when you accept a socket on that listen socket, you are basically doing this. You're sending back the acknowledgement, choosing your own sequence number, getting back an acknowledgement, and then at this point you have that handshake finished, and you can start doing communication. Yeah. Right. So, but the listen socket still exists to listen for additional SYNs from other clients, and that's how you can have multiple connections, a multiple connection server. Okay. Connection close is, I don't know how interesting this is really, but I have a couple slides on it. It's another kind of handshake thing. You have to tear down a connection in order for the to free up resources on both sides. So if you're done with the socket, you call close in your application, which you probably did in your code. And when you do that, that causes a fin packet, meaning finished, to be sent. And again, this is just a packet that has one of those bits is called fin, and that special bit is set. And then the server acknowledges that, and it sends its own. It might send its own fin. So actually, both directions of the connection can can be opened separately. I mean, they can't be opened separately, but they can be closed separately. So the client might be done sending its data, so it may close. The server may still have some data to send back, so it can stay open for a while, which is what happens here. So the client is done with its, let's say the client made a request, it's done, it sends fin, the server can acknowledge that, but it can still send data back, like it's still sending back HTML, and the client still has to acknowledge that data, because even though it closed the connection and the close was acknowledged, that only one direction was closed and that was acknowledged, and then finally the server can close the connection, and that should be acknowledged as well. So this is a half-closed connection. I'm not sure I really want to talk about these details. So this is a trace showing, this is again from the TCP IP Illustrated book, where there's a handshake, and then there's data sent. So the client sends 3 packets with 1,024 bytes 3 times, and I guess you can see the many different parts of the TCP behavior at once. So here, there's a delayed acknowledgement, although you would have expected this to happen right after this one, but anyway, it's acknowledging 2049. Actually, it is, yeah. So 2049 is this one. The delayed acknowledgement happens here, although it took some time to process it. This is acknowledging the second packet, because this goes from 1025 to 2049. I don't know if you can see that. And then it also acknowledges this one. And then more data comes and acknowledges that after a delay. This is probably the half second here. And yeah, this is also showing the window size. Okay, so in the handshake, the server, the receiver here, advertised its window size as 4096, and that means that when the sender has sent this third packet of data, its window is is 3/4 full. And when it sends this fourth packet, then the window actually has slid over 2 because 2 packets were acknowledged. And so these first 2 have already been acknowledged, and the window is now here. And then this one here fits in here. It still has 2 more it can send. It does that here. Yeah, I guess, yeah, question?
For the first 2 like data transfers, is it choosing like those 2 different numbers so that each side can send data to the other? They can send those separate acknowledgements to both sides?
You're asking about the handshake?
Yeah.
The number chosen on both sides is random, and it's not influenced by the number chosen on the other side. It doesn't matter if they are happen to overlap, for example.
It'll keep track that specific number was being received. It doesn't affect the data transfer to the other host.
Well, the TCP participants track sequence numbers in both directions, but in different ways. So you have to know what sequence number you should use for your next outbound data, and that depends on what acknowledgement you previously received. And then in the other direction, when receiving data, you have to know what the last valid packet data that you received, so you know what to acknowledge back in the other direction. So the numbers, and then on the other side, it's a mirror of the 2. They have the roles are reversed and the numbers are reversed. So they don't actually, they never influence each other, I guess. Yes.
Why did 77 only acknowledge 4 and 5? And not
7
6?
is here.
Yeah.
It didn't acknowledge
6.
this one. That's what you're asking about?
Yeah, why did
It didn't, so it's a little confusing here the way it's drawn, but this is an acknowledgement for this.
And
And this delay here, I think, is processing delay.
Gotcha.
So the software started to generate this acknowledgement,
Yeah.
and then but it wasn't sent until after it also received another one. So there were 2 acknowledgements sent. There's just a delay in response.
I guess why did it acknowledge 4 and 5?
When at time 7,
Yeah, it acknowledged 4 and 5 all at once, right?
it did acknowledge 4 and 5 all at once. You're asking why did it do that?
Yeah.
Not just
3.
4.
Well, so why did they acknowledge 2 and not 3? I guess that's what I'm asking. I know that there's processing delay.
Okay, so 3 was part of the handshake.
Yep. And then
That doesn't need to be acknowledged because there's no new data.
Gotcha.
4 is the first data packet, but then there are, remember there are delayed acknowledgements.
Yeah.
So this isn't acknowledged immediately, it waits half a second. The time is actually shown here, and this is 17 milliseconds and 22 milliseconds, so it's pretty fast. The second one comes in, and the rule says you have to send an acknowledgement.
Gotcha.
Yeah, and that's where this comes in.
Okay.
Turns out a third one comes in too, but then it already has started sending the acknowledgement before that happens. Okay. All right, this isn't maybe too important, but the protocol has to handle unusual timings of these packets being sent and received. Here's an example where 2 machines try to open a connection at the exact same time. So SYNs are sent at the same time, and there are rules for dealing with that. And same thing for simultaneous close. The rules are kind of shown in this flowchart, which is kind of a pain in the is complicated. So if you were implementing TCP, you would have to think carefully about all the different states. These circles represent different states you could be in terms of connection states. Initially, this is the starting point, everything is closed. And then you might start listening, or you might start an active open, in which case you send a SYN packet, and that puts you in this state, and so on and so forth. So I guess this is just here for reference. I'm not going to talk about it in detail. So I guess I didn't get through as much as I was hoping to. We still have a few minutes, but I'm just looking ahead. That's okay, because this is a big topic, and I think we have plenty of time in the class. So I will, I'm going to start talking about congestion control. Then I think I'll have to review it next time, and that's fine, because we'll have another lecture on TCP next time. So congestion is when the network is overloaded, and this is, in that situation, what I mean by the network is overloaded really means the routers have more data than they can handle, the router's queues are full, packets are dropped, or maybe packets aren't being dropped, but the length of queues on the routers is very long, and so even though packets are eventually making progress, it's taking a long time for the routers to get those packets out on the wire. And so you end up with long delays. And that's another symptom of congestion where data isn't lost, but it's taking longer to reach the destination than you would like it to. And one important point, which is not totally obvious, is that to motivate congestion control, why do we need congestion control? If we have mechanisms to react to dropped packets, we know that TCP will retransmit if a packet is lost. Why do we care? So I'm telling you why we care now. Because dropped packets lead to a lot of inefficiency and compound the problem. So what I mean is, if you have congestion, that by definition, that means you have packet loss. You have too much data on the network, packets are dropped. Packets are being dropped because there's too much data on the network. TCP will react by retransmitting data, which means you have even more data on packets on the network. And you have more congestion, and you have more loss. So it's like a vicious feedback cycle. And the reason it gets worse and spirals out of control is because if you're trying to send X amount of data, and it only gets through to the end 50% of the time, then you have to send 2x data, right? Because all the packets that you send that never get to their destination are wasted effort, and it's wasted it wastes network resources, right? So you have this is the start, this is the finish. If you just are imagining a very simple network with two hops in the middle, if you're sending data 3 times and you have some rate of loss, where sometimes 1/3 is lost, dropped here, and 1/2 is dropped here, eventually it gets through. You tried 3 times, it only came through once. All of this data, all of this traffic here was wasted. It doesn't accomplish anything because you can't. It's not eventually going to be able to get to its destination. Okay. So you want to prevent this negative feedback cycle, and so it's better to wait and not send anything if you know that packet's not going to get through. If you know this packet's not going to get through, it's going to be dropped here, you might as well just wait, because that means that other people will be able to use this link, or when you decide to use the link, it will have less backlog in the queue, right? And this is very difficult to solve, this problem, because you have many concurrent hosts using a path and many hops along the way, and you have no way of, the protocols are not designed to give you any visibility into the state of the routers. We only know the end-to-end behavior. We only know whether an acknowledgement comes back. Okay. So I guess I'll stop there, 1:50, and we'll resume next time. Well, actually, let me just see. I'll go through the recap that covers what we covered. So we talked about TCP. It's a combination of some elements of go back in, some elements of select and repeat, and my slide. So timeouts are computed based on exponentially weighted moving averages. Don't forget that. The connection setup requires a 3-way handshake, and flow control, which prevents overload on the receiver side, is implemented in an explicit receive window. Okay, we didn't talk about this last one. All right. So I'll see you next time.